Implicit differentiation. And this is the fun stuff. Yep. Let's go. So let's start off with something pretty mellow. Let's just go find this derivative. And we're asking to find dy dx. So typically having a lot of problems, they just start like y equals some garbage, or like f of x equals garbage, right? Well, let's go. Let's make it look like that. So let's bring this x cubed over. Track it over. Cool. Y cubed equals 5x plus 4, and then I'll put that minus x cubed on that at the end. Cool, and then, odd root. Let's just hit it with a third root. This is third root. And what's dope about odd roots is you don't need a plus or a minus. Actually, it can be negative. It's all good. So there we have it. Cool. Let's go find a derivative. Dy dx. Oh, hold on. That wasn't derivative, right? 1/3 power, huh? Maybe wanting to get more into the habit like this instead of going like, how do I unravel a third? Oh, we just put it to the 1/3. Put it to the 1/3. Cancels. Not this one. That one doesn't cancel. These two don't cancel because there's that plus or the minuses in there. Alright, cool. Well, let's do it. Chain rule. The 1/3 falls to the front. We leave the inside alone. We subtract 1 from 1/3, that's negative 2/3, and then we multiply by the derivative of the interior. The derivative of 5x is 5, the derivative of 4 is nothing, and the derivative of negative x cubed is negative 3x squared. And I think we could just leave it right here. I think that should be solid for right now. Cool. That's what we call solving explicitly. This is called implicit differentiation. This is what the section is called. So we're going to use a different manner to solve. We solve for y explicitly to where we can do this derivative. But sometimes y's are going to be inside of what we're messing around with. And we're going to need to use chain rule to get out of it. So typically if we were in class, I'd be like, all right, your turn. Go get the derivative. Let's go use try and solve for it explicitly. And go through and be like, all right, well, let's subtract that x squared on over to the other side. You know what I mean? Let's do one of those. So we get y squared is equal to 1 minus x squared. And then we go to hit it with a root, but when you hit something with a square root like that, you need a plus or a minus. And I'm purposely not writing this as the 1/2 power because I want us to be very careful with this. I want us to make this knowledge that we shall say that y is equal to plus or minus 1 minus x squared. Okay, if this ever happens, you end up, you got a plus or a minus. Stop, don't take a derivative. Don't do it. Don't just write plus or minus the derivative of that thing. It's going to be wrong. This is showing us something has gone horribly wrong. It's not even wrong, it's just the fact that this is not a function. Implicit differentiation is great for things that are not a function. Because of that plus or that minus. Let me show you that. I'll draw it in 2 different colors. Let's say y is equal to the positive of the square root of 1 minus x squared, and then we can have y is equal to the negative of 1 minus x squared. So let's look at these 3 pieces of information. This one and this one. Well, come on. Look up top. That's the freaking unit circle. It's the unit circle. A circle is not a function. Huh? Circle's not a function. That doesn't pass the vertical line test. Look. It's called the y-intercept. You know what I mean? It's the y-intercept. So this is not a function. But let's look at what y equals the square root of 1 minus x squared is. And it's just the top part. And then the bottom part is the negative square root of 1 minus x squared. So they actually create two different functions, right? That plus or the minus, when we hit it with the root, it's like breaking it up and being like, no, there's actually two functions. So if I was to tell you, all right, go find me the slope at, oh, this is 1 and 1 and negative 1 and negative 1. Sorry, I didn't put my scale in. At x equals 1/2, what's the derivative? What's the slope of the tangent line at 1/2? Is it this one? Or is it this one? They're both at x equals 1/2. Right through here, that's x equals 1/2. Which one is it? And you'd have to say, it depends on which y you're talking about. So when we do these problems, we care about the x and the y. They both matter because now it's not a frickin' function. All right, now let's solve it the right way. This is just saying if you get to this point and you're ever solving something, just be like, nah, start over. I need to do implicit differentiation. And let's intro it. So x squared plus y squared is equal to 1, and we want to go find dy dx, the derivative of y with respect to x. And this is how we're going to do it. Just go. We're ready to go. This is derivative ready at this moment. So let's do the chain rule on everything. And this will be silly because you already know the derivative of x squared is 2x, right? But just humor me. All right, so the 2 comes down. We're like 2 times, and we leave the x alone, and then we multiply by the derivative of x, and that's 1. All right, it becomes 2x. All right, cool. Now let's do the same thing on y. So we go, all right, 2 falls to the front, and then we leave that y alone inside of there, and then we go, okay, now take the derivative on y. Now it's not 1. It's not 1. Do you know what the derivative of y is? The derivative of y. It's what we're trying to find. This is what the initial question asked you, is to find dy dx. Find the derivative. It's right there. We're trying to find what's the derivative on y with respect to x. That's what this says. What's the derivative on y with respect to x? So it's wanting to give you a derivative that comes from something like this, but we're going to do it in a different way. So once you get to this, if you're ever taking a derivative on y, you need to multiply that shit by the derivative of y with respect to x because it's a freaking chain. And we'll continue moving. We move on to our next, and we take the derivative of 1, and that is equal to absolutely nothing. So now we clean it up. We get 2x plus 2y times dy dx is equal to 0. The game becomes solve for this. Solve for dy dx, and that's going to be your answer. And your answer is now going to have y's and x's in it because we got to know the frickin' y value. We don't know the y value. We don't know whether we're dealing with this one or this one, right? We wouldn't know. So when we go to solve for this derivative, it'll have x's and y. So let's subtract the 2x over negative 2x. So you get 2y dy dx is equal to negative 2x. We divide out the 2y, and we get that the derivative on y with respect to x is the 2's go away, and we just get negative x divided by y. And there's this derivative saying all you need to do is take your x value, change the sign, and divide it by your y value. And we'll get the slope of the tangent line anytime you want. So let's take a look. Let's go find it, and let's use this notation for what we just messed with. We're going to go, we want to find the derivative of y with respect to x. And now I can't write x equals. I actually have to give you an ordered pair. An ordered pair, I need to give you an x and a y. So how about like 1/2? And what would be the other y value? Let's go with the positive one first. So y is equal to 1 minus the square root of something squared. We're plugging in that 1/2. I wonder what that could be. 1 minus a fourth. I'm not going to show any steps on this. Well, not all the steps. Square root of 3 over 2. Weird, like 1/2 and square root of 3 over 2 go together when we're talking about trig. So now we're saying take the derivative when x is equal to 1/2 and y is equal to root 3 over 2. And we go through and we can just use our formula there saying change the sign up top, so our x value is going to be negative 1/2 divided by that root 3 over 2. Goes away and we get negative 1 over root 3. It's like we were finding tangent or something. So we found out the slope up top is negative. Huh? Does that make sense for this point here where we took the positive? Now let's do the same frickin' thing, but let's take the dang negative. Let's go find that derivative on y with respect to x, but now let's go with 1/2 comma negative root 3 over 2. This point, the one that has the positive slope. So now when we go to plug it in, you get that change the sign of your x value, negative 1/2, over your negative root 3 over 2. The signs cancel, the 2's cancel, and just leave you with positive 1 over root 3, saying that the slope is frickin' positive there. Huh? Implicit differentiation. This is the game. This is what we're going to do. This stuff is going to get algebraically dense. I mean, dense. I'm going to be coming at you. I got a few problems where they're almost a full frickin' page just written out. So let's get ready for algebra. This is where we really show off those skills. All right.